The majority of people know about large deviations, but not the 90% of us. So I thought it made sense to give us a quick reminder of how this works. And also, even for those of you who already know that, I think I'm going to present it in a way which is perhaps slightly different from the most standard. I mean, overall, it's going to be not too surprising, of course, but okay. Just the exact statement I'm going to write down is perhaps slightly different than usual. But anyway, so I guess the basic question is when we take independent, identically distributed random variables, maybe I'm going to, like this. So independent and identically distributed real random variables. And we can look at the sum of so let me add a hypothesis that they are not having two fat tails. And I'm not going to shoot for the most general possible statement today, okay? I just want to give you a flavor of how things look like. So I'm going to assume that they have exponential moments at every order. Okay, so for every lambda in R, when I compute this exponential moment with the lambda in the parameter, this is finite. Okay? So let's say that they are bounded, if you like. And also, let's say that they are centered, otherwise we could just subtract the mean. And if I take x strictly positive, so we know that if I take the sum of these random variables and divide by n, like if I sum n of these random variables and divide by n, we know that this is supposed to converge to 0. And the question that large deviations is asking is what's the probability that this is really away from 0? So let's say greater than or equal to x, where x is a strictly positive number. And we're trying to estimate this. So if you've never seen this, and you try to estimate what this probability looks like, maybe one first idea you can have is to use the sort of Chebyshev or Markov inequality, I don't know how you call it, where you can compare this with using the variance of these random variables, for instance. And you could write, okay, this is going to be smaller than the variance, or it's the second moment of the sum divided by n squared x squared. And this, it looks like n times the second moment because they are centered. And so you get an estimate which is of order 1 over n as n becomes large. And you can ask if this is sharp. And if you ask yourself if this is sharp, you notice that when you put the power of 4 here, for instance, you can still write this inequality. But then, okay, you do your calculations, and you will find a decay of 1 over n squared instead of 1 over n. So you start to realize that 1 over n was not the right choice. And then you start to wonder, but what is the right choice? And so then I'm going to erase this. And I'm going to write a better inequality. So instead of playing with polynomials, now we start to feel that it should decay faster than the polynomial. So maybe we should try with an exponential instead. So maybe I'm going to also select a parameter lambda, strictly positive, and I kind of hinted already at what I want to do. I gave you the hypothesis for doing the right move. So instead, we can write that this is exponential of lambda x1 plus blah, 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 plus xn divided by exponential of lambda x. Okay? And I forgot an n. Okay, that was the point. Okay, now this has some perhaps chance to decay like exponential of n. And the key aspect I want to do here is that these are independent. So I have, the exponential of the sum is the product of the exponentials. I use the independence. And so then this is some fixed function to the power of n. This function is actually just that quantity to the power of n. So let me rewrite it like this. So this is equal to what is on top. So minus n times and then I have the lambda x in the denominator, minus, I'm going to denote this as psi of lambda, and I put the parentheses correctly. Whoop, whoop. Great usage of the board. Where psi of lambda is defined to be the logarithm of that object. So log of expectation e to the lambda x1. Okay? And if you look at psi of lambda, you see that, okay, psi of 0 is 0. And if you Taylor expand around 0, you see that it wants to look like the expectation, like lambda times the expectation of x1, which is 0. So the first order part of this psi is actually 0. And then you will have some parabola related to the second order expansion of this function is going to be a parabola with opening given by the variance of x1. I'm not going to do the calculation, but so you see that if lambda is small enough, because x is positive, this is going to be the dominant term in this expression. So you can make this term really strictly positive. Okay, so this already shows that the this decays at least exponentially fast as n goes to infinity. Okay, because you can see that you can select lambda to make this quantity strictly positive. But in fact, while we're at that, we can inquire about what is the... So I claim that the exponential order of decay is the right order, and then you can explore what is the best constant you can put here. So now instead of just, observing, we can select some lambda which gives this positive. We're going to optimize over lambda. Okay? And maybe before I do this, let me observe that this function psi is convex. Okay? So this is also an easy exercise, but c'est lemma. The function psi is convex. So I'm going to give you a proof because I'm going to use this fact a lot of times. And the proof is very short. So what do I do? Okay, I keep to use this French notation for the open interval because why not? Sorry, maybe I should write like this. So I'm supposed to compare this with the product of this guy to the power of alpha, this guy at mu to the power of 1 minus alpha. And so, okay, I write this exponential of a sum as a product of exponentials. And I see what I want to do is raise each of these terms to the power, well, one at power 1 over alpha, and the other at power 1 over 1 minus alpha. Okay, and that kind of reminds us of Hölder's inequality, and you can observe that indeed you're in a good position to apply Hölder's inequality here. Okay, so if I do this, I'm going a bit quick because it's supposed to be a little bit more standard, I guess, but I hope you can still follow something. Okay, so this is by Hölder with exponents p equals 1 over alpha and q equals 1 over 1 minus alpha. Okay, you can observe that 1 over p plus 1 over q is equal to 1. Does that make sense? Now, if you take the logarithm of this expression, you get the convexity that was claimed. Okay, and part of the reason I wanted to display the proof is that I want to also observe that this also is going to work in case x1 is vector valued and lambda is vector valued, and you take the scalar product between the two terms. You see, you can just copy the proof. Okay, so remark also works if x1 takes values in Rd. This is a D. And lambda also takes values in Rd, and then we write the scalar product in the exponential, okay, where there was the multiplication. Okay? And be mindful that this looks a little bit like these free energies I was writing before, like yesterday. So there was this function of beta yesterday, for instance. If you think about this, this is a proof that this function of beta is convex also, as a function of beta. And if we have more variables, it will be jointly convex because of this remark. All right, here is this. Okay, so why did I say all this? I was in the middle of this calculation, and I was saying, oh, we should optimize over lambda here, right? Maybe I'm still going to erase it, but okay. Remember the bound is that thing. Maybe I'm going to just keep that displayed. Oh, it looks like I planned it. Okay, so let's look at this object. So let's define psi star of x to be what we get when we optimize over lambda in this expression. And in fact, in this calculation, I had only lambda positive, strictly positive, but in this definition, I'm going to optimize over all lambda. Lambda x minus psi of lambda. So again, I hope that many of you recognize that this is the convex dual of the function psi, which we showed is convex. Some call it Fenchel-Legendre also, or, well, whatever. In particular, this is a convex function as well, because you can see that it's a supremum of affine functions. So in particular, it's a supremum of convex functions. So it's convex. I guess from the definition, we can also see that if you do Jensen's inequality, you can, and then use that x1 is centered, you can see that, also remark, let's say, by Jensen, psi of lambda is non-negative. Okay, so I want to, I write this because I want to argue that when x is positive, it doesn't really matter if you optimize over lambda positive or over every lambda. So let me explain this. So observe, let's say. So lambda negative. Okay, so recall. So this is a definition that I take as valid for every x. Okay, but now if I'm back to the calculation I had done at the beginning, in the calculation at the beginning, so maybe for x, I should write it. For x positive, we have that when I optimize over lambda negative, this is just negative, and then psi is positive, there is a minus sign, so everything is negative, and so this is negative. And in particular, well, when I take lambda equals 0, I just get 0. So in fact, this is equal to 0. And if x is positive in this definition, I can take lambda positive. I don't lose any generality. Okay. So just this simple calculation, this simple Chebyshev with the exponential function, gives you that. So we conclude that the probability that 1 over n, the sum of these variables being larger than x, is always smaller than exponential of minus n times psi star of x. Okay, and we did this derivation for x positive, but if x is negative and I inquire about the probability that this is smaller than or equal to x, then the same inequality will be valid. Okay, so this was very cheap, very easy. I mean, we didn't make much effort to derive it. And the remarkable fact is that this is, in fact, the sharp constant in this inequality. In the sense that if you take the logarithm of this probability and you divide by n, this is going to converge to psi star of x. Okay, and this is a non-trivial claim, and this is the content of Cramer's theorem. I'm going to state it more precisely. But let me erase first. So one very simple observation I want to make before I state, before I say some more, let's say, important things, is that when we look at events like this, events that have very small probabilities that are exponentially small in n, then there is some, let's say, there is some interesting behavior that occurs. For instance, so let's say simple observation. If you're looking at a random variable, let's say Sn, a family of random variables, think of Sn as maybe being this normalized sum as an example. And let's say that you know that the probability that Sn belongs to some set behaves roughly like exponential of minus n times little a. A is some set. Whoops. That was an interesting move with the mic. I hope it's still okay. The mic is still working? Yes. Okay, awesome. So let's say there's some number a and some set a such that this occurs. And suppose you also know that this behaves like this for some other set b. Then if you inquire about the probability that Sn is in the union of a and b, this is just going to be given by the minimum between, or maybe I should write min, between a and b. Okay, because if you use the union bound, you'll have the sum of these two exponentials, but at the exponential scale, it's just going to be dominated by the parameter that is smaller, and the converse bound is just easier. You just decide that maybe if a is the best, you just upper bound this by the probability that Sn is in a. Okay, and so this is a very simple observation. But the important aspect that I want to emphasize is that, let's imagine that, let's forget about uncountable sets for a second. Let's say a and b are finite. You don't need to remember the shape of a in order to understand this question. You just need to know basically the only element which Sn is going to pick in order to satisfy this probability. Okay, and if I come back to this calculation, when we compute the probability of this event, we're just asking probability that is greater than or equal to x. It could do a lot of things being greater than or equal to x. But in fact, if you condition on this event, this random variable will be basically equal to x. Okay, maybe it's going to be x plus a tiny bit, but this tiny bit will be going to 0 as n goes to infinity. Okay, and so in order to, and this is very interesting because we, in some sense, things simplify in this way. We just need to describe the function for any point, what is basically the probability to be at that point, plus maybe like a little blur around this point. Okay. So that leads to a definition of what it means for a sequence of random variables to satisfy a large deviation principle. And we have in mind as the key example the thing I'm just erasing. So now we are back to remembering that there are sets that are uncountable, so I'll be a little bit more careful in my definition. And I'm just going to take random variables that take values in R, okay, because I just want to do simple things. So we say that the sequence of random variables satisfies a large deviation principle. So maybe I'm going to write like this. Maybe this is, with rate function I, if the following two things occur, for every set A, okay, measure our set. So first point, what do I like to start from? Maybe I'll start with the upper bound. I forgot the log, of course. So here there is a log. 1 over n log of the probability that Sn belongs to A. I'm asking that the lim sup is bounded by, well, the minus the infimum of this rate function I of x in, I'm going to take x not just in A, but in the closure of A, just to be sure. So this is A bar, this is the closure of A. This is the large deviation upper bound. And now the lower bound. This time I'm going to write the log directly without messing it up. 1 over n log probability Sn belongs to A. We're going to ask that is greater than minus the infimum of this same function I of x. And again, just to be sure, instead of just taking A, I'm going to look at the interior of A here. Okay, I give myself a little bit of margin. Okay, so here A bar is the closure of A. A with the little circle is the interior of A. Make sense? Okay, this is the, it's easier to satisfy this inequality if I add the interior guy, okay? Yeah, so I wrote in parentheses with speed n, because sometimes it's kind of useful. You already have your sequence at hand. You don't want to change the way it's indexed, but you would like to change that guy. Okay, so the speed n is indicating this guy. Well, we're going to only discuss speed n things, so not to worry about this. And so the claim of the large deviation theorem for sums of independent random variables is that when Sn is this normalized sum of x1 up to xn, we can take I to be psi star. That's the claim of the large deviations. It's called Cramer's theorem. Right. So this is, very classical. I'm not going to give you this directly, in fact. I'm going to give you a more general version of the large deviation principle. Instead of just giving you this Cramer's theorem and giving you the proof of it, I'm going to give you something a little bit more general, which is often called the Gertner-Ellis theorem, I think. But yeah, like the statement can be made more general than the way I'm going to state it. And so maybe Gertner-Ellis would be the really full, the full generality maximal thing. And I'm going to try to strike a balance. This is why I was saying this is perhaps not exactly the way you're used to seeing it, because I'm kind of trying to find the balance that works well for what is going to come next for us. All right, so yeah, the claim is that when we did our calculations for this normalized sum, really what we used is that we could compute the Laplace transform of Sn. We could do it explicitly using the independence and blah, blah, blah. But in fact, really what matters is that you can compute it. It doesn't matter if it's by independence or whatever. So instead, my assumption will just be you can compute it, and you can understand the limit. So let Sn be a sequence of, again, real valued. Okay, they take values in R. This is an S, even though it doesn't maybe look very much like it. Rubbers. And let's for every lambda in R, we're going to set psi n of lambda to be, maybe this is not a good use of my board, psi n of lambda to be, maybe I should, yeah, 1 over n. 1 over n log exponential of e to the lambda n Sn. So you see, if you think of Sn as being the normalized sum, then the n is like removing the normalization. So you just have this sum of random variables, and if you use independence, you see that this does not depend on n. Okay, so it's a nice, smooth, convex function in this case. And in particular, it converges because it doesn't change as n varies. But here, our hypothesis will be that this converges to something decent. So suppose that psi n converges to some function psi. And by this, I mean pointwise. You know, for each lambda, you have convergence of psi n lambda to psi of lambda. And the key hypothesis is that psi is a function that is, well, I'm going to assume it's finite for every lambda. This, again, could be weakened, but we're going to be happy with this. Where psi, and in fact, I'm going to assume it more than just that it's finite for every lambda, because I'm going to assume it's a C1 function of lambda. Okay, so again, if you think about independent random variables, then it does, you know, it's just psi1. It doesn't depend on n. It's clear it's a smooth function, no problem. But in general, I'm assuming that this is a C1 function. And if this assumption is satisfied, I claim that what you're expecting now, I hope, is valid. Okay, the large deviation principle is true for Sn, and the rate function is psi star, this convex dual of function psi. Okay. Is there a question? Maybe I should say a large deviation principle. I don't know. Okay, I don't know if I should say A or D. Anyway, the large deviation principle, okay, LDP, I'm writing here. With speed n, I'm not writing, and rate function. Psi star, okay, I remind you that psi star of x is defined to be the supremum over lambda of lambda x minus psi of lambda. Yeah, exactly. Yeah. So we know in advance that psi is convex. And by the way, yeah, I also want to say, you can take the convex dual of any function if you like. What's interesting, if you know in advance that psi is convex and defined everywhere, is that if you yet again take the convex dual of this guy, you get psi back. Okay, this is the Fenchel-Morrow theorem, that the bidual of a convex function defined everywhere on R, like with finite values, is the convex function itself. Maybe a bit to it. All right, so now my goal is to give you a sketch of proof of this statement. Are there questions on the statement? So I'm going to comment later on the C1 assumption. At least we're going to see it plays a role in the proof. And then I'm also going to try to convince you that it's really necessary. It's not just because I like to use it in the proof. All right. I was wondering where my notes were, but they were in my hand. That's a very mysterious place to be. Okay. So sketch of proof. I claim that basically the upper bound, we have done it. Okay, you just rerun the argument that I gave you for sums of independent random variables. And yes, it's true that the way I stated the upper bound here was kind of more complicated with a general set, etc. But okay, you can, first you can observe that it suffices for you to show the statement for the upper bound for a closed set, because you just have the inequality going in the good direction if you replace A by the closure of A. And then you can decompose the closed sets into parts, or you can make some moves. It is not difficult. It just takes time, but it's all in the notes, by the way. And so don't worry if you don't like. So I claim that the upper bound is basically already done. In particular, here we do not use the C1 assumption. Okay, whatever psi is doing, the bound is going to be valid. And also, the way we state these bounds, they are like, we take 1 over n log, etc. But when we do the upper bound thing, we actually get it without all of the asymptotics aspects. So you just get the bound. Okay, so really the question is the lower bound. So for the lower bound, again, I allow myself some imprecision because I told you it's a sketch of proof. So I'm not going to prove it for every set. Again, in this case, you can assume without loss of generality that your set is open. And then basically you just want to focus on around one point and say, if you draw a little ball around the point, then you can do what this lower bound is saying. So we're going to show something like this, at least give a sketch of proof or something like this. We aim for. So how should I say that? So 1 over n log Sn. So I'm going to just take a point x in R and give myself a little ball around x. Okay, my balls are inside R, so it's just this open interval. And so I'm going to ask myself about probability of this event. And hopefully, we're going to show that this is greater than minus I of x. Okay, for every x in R. And this will be, I just need this. Okay, I want to make sure that this works for every epsilon. So I'm going to do something like this. Okay, I want that this is valid. Make sense? All right, so let me make a few simple remarks. I'm going to start using the C1 assumption here. So psi is, okay, we don't really need to use that it's convex, but in my head I think about it, so let me write it. But more importantly, it is C1. So when I look at the image of psi prime, is going to be an interval of R. Okay. You see, psi prime is increasing, so and is continuous. So it's kind of clear that the image of R by psi prime is going to be an interval. And let me call the endpoints D minus and D plus. Okay, so I don't tell you if the interval is closed or open. I don't tell you if D plus is finite or is infinite, but I just give names to the endpoints of the interval.
Eventually it might be minus infinity plus infinity.
That's right. So the first thing, again, I'm going to be a bit sketchy on this, but the first thing I want to observe is that, let's say that, for instance, D plus is finite. Let's say it's 1. Okay, so it means that everywhere psi prime is bounded by 1. So in particular, if you think about the growth of psi, it cannot grow faster than lambda, okay, because the derivative is bounded by 1. Okay, so it's going to be smaller than psi of 0 plus lambda. Okay, that has to be true. And so if you try to compute this function for x greater than 1, you're going to get plus infinity as a result, because you have, let's say x is 2. You get 2 lambda minus something that cannot go faster than lambda. So this is going to be plus infinity. Okay, so whenever the x we are shooting for is exceeding d plus, this guy is plus infinity, and what we're trying to show is obvious. So very good. Okay, so let me write it here. So if x is greater than d plus, well, maybe d plus is plus infinity, but okay, if it's finite, maybe x can be like this. Then psi star of, I of x. Oh, I meant psi star here, of course. Sorry about this. Then psi star of x is plus infinity. Okay, so nothing to do. So all good. Okay, and similarly, if x is strictly below d minus, no problem. Now, okay, if x is at the endpoints, okay, you have to be a bit careful, you think about it, but because we have this epsilon of room, in fact, as long as we can deal with x which is inside the interval, everything will be fine. So this, again, sketch of proof, so I allow myself to be a little bit vague on this, but I hope it's plausible at least that if you know that the statement is valid for x inside the interval, then because you have this epsilon of room and you think about the properties of psi star, you can manage this. Okay, so let's assume that x is inside the interval. And really what I want to assume, in fact, is that I can find a lambda such that psi prime of lambda is equal to x. Okay, these are the endpoints of the interval which represents the image of psi prime. So in particular, whenever x is like this, I can find lambda that is such that, let me write it, we can find lambda psi prime of lambda equals x. Okay, and why do I do this? It's because, well, we're trying to show this inequality where psi star is defined as an optimization problem. It's written here. And what is the best value of lambda? This is what I should be concerned about. Well, if I look at this, we're going to see that, just take the derivative in lambda in this expression, you get x equals psi prime of lambda if you set the derivative equal to 0. So you see that the best lambda possible should satisfy x equals psi prime of lambda. And so now we have our selection. We have made sure that we can select lambda that is like this. Okay, and so now we are ready to try to think about this. So we have selected our lambda, and we're starting and trying to estimate this probability that Sn belongs to this small interval around x. And maybe we are not very inspired, and we only remember how we did the upper bound. So what can we do? Maybe we try to do a little bit of the same thing sort of Chebyshev, but with the converse inequality. So it looks like a nice move to do because at least it will make this psi of lambda appear. You know, I will have exponential of lambda n Sn, and then I have to compensate, or maybe I should write the indicator function of Sn being in this interval. Yeah. Okay, and then times exponential of minus lambda n x plus epsilon, I guess. Like this. Sounds good. And now it would be really nice if we could just remove this indicator function, because this would be looking like psi of lambda in this exponential multiplied by n. And here we would have lambda x, and so we would have exactly lambda x minus psi of lambda. Okay, so really, does that make sense? I see. Yes. So really what we're wondering now is that, you know, we try to make the right moves, select the correct lambda, etc. Did it allow us to make sure that, was it, you know, nice enough that, in fact, in this expectation, let's say, on the relevant event that gives the contribution, the important contribution for this exponential, actually this event is happening by default. Does that make sense? I want to say, so we would like, maybe let me write this. We would like that this is really the default situation in this calculation. And so maybe I'm going to write the converse and say that when this exponential is around, if I wonder, if I also force Sn to not be in the interval, then this is really detrimental. So by which I mean this is going to be very small compared with just the vanilla expectation with no indicator function. Make sense? If we can justify this, I claim that everything will be fine. And in fact, I write very small because we're going to prove this. But you know, if it's just smaller than 1/2 of what is on the right-hand side, this would already be good for us. Okay? We're going to show it's very small in the sense of exponential separation, but this would be good. And I wrote it like this because, yeah, in this proof, I'm not being very imaginative. I only try to copy the upper bound that we have been doing at the beginning. And now this looks like an upper bound again. Okay, there's something, and we want to say it's very small. So I'm going to again try to mimic our proof for the upper bound, because now it looks like an upper bound question again. Yeah, so maybe let me say that here, implicitly here, I'm using that lambda is positive. So let's just, otherwise you just have to do the inequalities differently, but just, you know, for definiteness, let's say that lambda is positive. Okay? Otherwise, I just have to revert the inequalities. All right. So now, I'm going to try to prove this sort of upper bound here, mimicking the previous thing we have done. So I'm going to, again, try to do some Chebyshev with some exponential moment. Let me e to the lambda n Sn, indicator that Sn is greater than x plus epsilon. Okay, I want to bound this first, just focusing on one of the two possibilities for Sn to be outside of the interval. Let me see. Sorry, implement this. Yeah, just drop it down. Okay, so now what should I compensate this for? Minus mu n x plus epsilon. You check if I'm doing things correctly or not. Yeah, I tried to write my upper bound using a new parameter mu, which I'm going to optimize over again, like in my proof for my upper bound. Okay, lambda is fixed now, given by this. So maybe I can rewrite this as exponential of minus n times mu x plus epsilon minus, and this is psi n of lambda plus mu. So far, so good. Okay, so what do I want to do? And let me remind you, you want to compare this with what is on the right-hand side, with this guy. And if you write in this exponential of lambda n form, this is exponential lambda n psi n of lambda. Okay, so you want to compare what is inside this square bracket with psi n of lambda. You'd like to say that you have some margin. And the reason you hope you have some margin is because there is this extra epsilon here, okay? You think, in truth, Sn would like to be equal to x when there is this exponential around. So maybe because there's extra epsilon, you can say this is small. So this is our best friend, okay? This guy is our friend. This is where we have to get room. You know, this is our room for winning. And imagine you do a Taylor expansion of this guy now. So at first order, or at 0th order, you have psi n of lambda. This is what you want to compare with. And then at first order, you have psi n prime of lambda, which basically is kind of like x, okay, times mu. Okay, so you have mu x, and here you have another mu x. Okay, so they want to compensate. Psi n of lambda, this is what you want to compare it with, and this is your friend, so we should be able to win in this situation, right? And for us to win, we have to say that I can do a Taylor expansion of this guy, and it's kind of reasonable. And that's where the C1 assumption is crucial. Okay? So now I'm going to try to write down a little bit more of, select the mu and find the n large enough, etc. But this is the proof.
Now we also assume that psi n is the C1.
Ah, yeah, I'm going to try to be smart and not use that. Yeah, I'm going to only use that psi is C1. Good point. Yeah, in my sketch, I was a bit too sketchy. So, yeah, let me be a bit more precise. So, let's say first, let's select mu positive, but sufficiently small that we can have this working, but for psi. So that psi of lambda plus mu minus psi of lambda minus mu psi prime of lambda, that this is really small. And so remember, we want to win against mu epsilon is our friend, so I want this to be smaller than mu epsilon, and let me take some margin. So let me say this is smaller than epsilon mu divided by 10. Okay, so I can do this because the function psi is C1. Okay, so I know that this should be little o of mu as mu goes to 0. And so in particular, if mu is small enough, this kind of constant is supposed to go to 0, like this prefactor is supposed to go to 0. I can make it be smaller than epsilon over 10 if I like. Okay? So here I only use the assumption for psi. And now I'm going to use pointwise convergence of psi n towards psi. Okay, and remember, I'm erasing it, but this guy is x. Let me write it. so what do I do now? So now we have chosen our mu. And so I'm going to take n large enough. So let's take, now find, yes. Let me wait for a little. It's a good time to think carefully about whether I did the correct moves. Yes, I think it's okay. Okay. Maybe I should have a dry one, which I could kind of sweep a little bit. I'm not sure if I'm really helping here. Okay. So what do I want to do? Let me start in words. I'm going to choose, so mu is fixed, and I'm going to choose n large enough that psi n of lambda plus mu basically is the same as psi of lambda plus mu. And so then I can use this comparison. And then, okay, in this comparison, there's psi, and if maybe I wanted to shoot for psi n, so maybe I also assume that n is large enough that psi of lambda is close to psi n of lambda. Okay, so you understand the argument, so it's okay if you don't see it, right? So now mu has been fixed, okay? So if I like, I can take it like this. Oops, not what I said. It's good that I say it before I write it. I just was thinking that we want it at the two places, so then of course I messed up. Okay, is that better? That sounds right. Okay, and now you see that if you put everything together, we're just in business. We conclude. Okay, so what do? I already said it, but we replace this guy by psi of lambda plus mu. We replace psi of lambda plus mu by its Taylor expansion. And then we replace psi of lambda by psi n of lambda. And we lose a small multiple of epsilon mu over 10, maybe 3 times or something. So I get minus, n psi n of lambda minus epsilon mu over 2, let's say, and then n. So in particular, this is very small compared with the case when this is not present, which is just exponential lambda n Sn. Okay, this was our, what we were shooting for.
So there is a minus n, psi n lambda, minus n.
Epsilon mu divided by 2? I don't know which of my characters is worse written, so I don't know which I should erase first. Is that better? Maybe all of them. Okay. Is it good? Are you convinced? So now once we have this, did I make a mistake again? You're good? Okay. You tell me. Huh? I think the strategy is sound, but you have to check. Okay, so we have this. What we were really shooting for is that thing with indicator function that Sn is not in the interval, but you can imagine that the other bound is really the same. Like you have the room, the space in the other direction, and I'm struggling with writing stuff, but in particular inequalities that are tricky for me, so I'm not going to try to do the other way around, but it's really the same.
So there is a minus in front of n, or it is a plus?
Yeah, this is minus. So at first we had this minus n mu epsilon, and this is our friend, we want to keep it. It's going to be a little bit destroyed by these guys, but I think we're going to have a part which we don't like, which is plus 3n epsilon mu over 10. And so at least we're going to have a leftover minus n mu epsilon over 2.
So then at the end there is a plus. And a minus.
Like this, no?
Okay.
We're good? Here there's no minus. I didn't put the brackets here, so minus and like this. Are there other questions or corrections to what I have written? Good. Okay, so then we can do, we can control the other side of the interval. And this is what we were shooting for. So, okay, so maybe I can wrap up very quickly. Let me remind you how this whole calculation started. So we were calculating the probability that Sn belongs to x minus epsilon, x plus epsilon, and we said it's larger than expectation of E lambda n Sn with this indicator function. Times exponential of lambda and x plus epsilon, I think, with a minus. I think it's like this. And now we know that we can really remove this indicator function here. Okay, this is greater than e to the lambda n Sn times a very tiny thing. Okay, 1 minus 2. Something exponential in n, okay, minus, okay, I don't really care now, I just want to put 1/2 here if I like, okay, something positive, mu epsilon over 10 or something, or 2, times x of minus lambda n x plus epsilon. Okay, so this is in the limit, once we take 1 over n, the lim sup, of 1 over n log probability that Sn is in this interval, we're going to get that it is greater than, so this is going to go to psi of lambda to have minus lambda x plus epsilon plus psi of lambda. Okay, and this is really what I wanted.
You want the limit?
Thank you. Thank you. Absolutely right. So in particular, this is greater than minus the supremum over, let's say, lambda tilde of lambda tilde x plus psi of lambda tilde up to some epsilon, which is like this, minus lambda epsilon. Okay, and this is psi star of x. So we are happy. Okay, so this is the end of the proof, of the sketch of proof. All right, so in the last few minutes that we have today, I would like to do at least one thing, hopefully more things, but at least I'll start by trying to convince you that this assumption of regularity of this function psi is really necessary. That things can go wrong if you don't have it. So I'm going to give you an example. And I'm going to, you see this is a warning to tell you that psi should be C1, this is important. All right. On the C1 assumption, let's say. I'm going to give you an example where we can see that this is really important. And I have to say in advance that maybe the example will be a little bit confusing because I'm going to choose Sn which does not depend on n, which of course it is not meant to be the way you use this statement. But okay, you know, it's allowed, it's part of the possibilities. So choose Sn. To be like so. So Sn is equal to 1 with priority 1/2 and minus 1 with priority 1/2. And I insist that I'm not summing these variables. Okay, this is Sn. That's the random variable. Okay, so perhaps maybe if we try to think about what should be a good rate function for this sequence of functions, of random variables, well, we see that it can only take two values, 1 and minus 1. The others are impossible. So maybe a good rate function would be a function I that is 0 at 1 and minus 1, and it's plus infinity otherwise. Okay, because these are possible values. It's not even costly to be there. And otherwise, it's absolutely impossible. It's not even exponentially unlikely. It's really impossible. So plus infinity sounds like a good candidate. So maybe I'm going to write it. So I of x equals 0 if x is plus 1 or minus 1, and plus infinity otherwise is a good large deviation rate function. For Sn. Okay, but now let's see what happens if we try to apply our the large deviation principle we have just seen on this case and ignore this C1 assumption. So we have to compute these Laplace transforms. So psi n of lambda in this case is 1 over n log expectation e lambda n Sn. This is the definition. And so in our case, it's 1 over n log e to the lambda n plus, I forgot the 1/2, e to the minus lambda n 1/2. So you see, as we already discussed with this a and b calculation at the beginning, when you have this sum of exponentials, what will matter is the greater of the two exponents. So in this case, the maximum between lambda and minus lambda, also known as the absolute value of lambda. Okay, so this converges to absolute value of lambda, which by definition then is our function psi of lambda. So we have this nice convergence at every single lambda of psi n of lambda to psi of lambda. But of course, as announced a little bit, psi of lambda is not C1. Okay, you have a corner at 0. And if we apply if we calculate the convex conjugate of this function psi, we are going to get sup over lambda in R of lambda x minus absolute value of lambda. So if x is between minus 1 and 1, you'd better choose lambda to be 0. Well, okay, if x is 1, maybe you don't have to choose lambda to be 0, but you still don't win anything. So this is 0 if x is in the interval minus 1, 1. And if x is above 1, let's say x is 2, for instance, then clearly this is going to be plus infinity. Okay, you have sup of 2 lambda minus something. So plus infinity if x is not in this interval. Okay, and well, this is not what we were hoping for. We see that this is not a valid large deviation rate function, because if this was the rate function for our sequence Sn, in particular, it would predict that we have a not too small chance of falling inside the interval minus 1/2, for instance, okay? Because it says that this should be greater than, let's say, something which is like this, exponential of minus little low of n. Okay, on this interval, the rate function here is 0, so it tells you it should be You don't even need to put a small parameter here, okay? Like there's no strictly positive number you have to put. It should be little over n inside the exponential. Okay, but we see that this is not true, okay? This is absolutely 0. In particular, it's not greater than exponential minus little over. Okay? We had kind of announced it, okay? We said the sort of function we are hoping for should be plus infinity inside on minus 1/2 in particular. Okay, so it's not working. And perhaps a way to try to understand why it's not working, for which perhaps will only speak to people who understand convex analysis a bit in advance, but let me try to explain it. The thing is that when we calculate this object, you can try to think, imagine you try to decompose it into all the possible values of Sn, using that you know in advance that it satisfies a large deviation principle. Let's say I tell you in advance Sn satisfies a large deviation principle with rate function I. When you compute this, in fact, what you're doing is calculating the convex dual of the rate function already. Okay, you see you have this lambda, and then you'll have some I, because if you ask yourself, if you try to imagine that Sn is going to be basically equal to x, for instance, you're going to have exponential lambda n x minus the cost of being at x, which is minus n times I of x. Okay? So basically, this function, in fact, in some sense, is calculating for you the convex dual of the rate function. And then you're hoping that if you take the convex dual of the convex dual, what you see is the rate function. But when you take the convex dual of the convex dual of a function, what you get is the convex envelope of the original function. Okay, so in particular here, we had this function here, which is 0 on these 2 points and plus infinity otherwise. The convex envelope of this function is exactly what we got, is 0 on the full interval minus 1, 1, plus infinity otherwise. Okay, and so in general, when you compute this and then the convex dual, you get, let's say, let me write it like this. This is a bit of an informal discussion, but when you compute psi and you compute then the convex dual, what you're going to recover in general is the biconjugate of the rate function. And then you hope for a criterion that guarantees for you that when you look at this, in fact, you don't just get the biconjugate, but you get the rate function. And so if you know that that this function is strictly convex, that it has no flat piece, then let me emphasize. Let me do a few drawings for what a convex envelope looks like. So, okay, basically our rate function in the example looks a bit like this. Okay, it's a bit of a cartoon, but this is like an enlargement of the points minus 1 and 1. And then when we take the convex dual, this gets bottomed down, and this is the convex envelope. Okay, so in general, if you have a function like this, the convex envelope will be just trying to squeeze like this below. Okay. So imagine that I only show you the convex envelope of a function, and I ask you, can you recover what was the original function? Well, here you can recover because it's bending. So you know that when I show you the convex envelope, you know you're actually seeing the true function. But here it's not bending, so you're not sure. Maybe it's the true function. Maybe the true function was just following this perfect slope, but maybe it's not the true function. Okay. And when the assumption that psi is C1 guarantees for you that psi star is always bending, in fact. It's always a little bit sloping, like the slope is always varying a little bit. So you know that psi star is, you know that even though you're only shown the convex envelope of the guy, in fact, you know it is the guy. Okay. Okay, this was a bit informal, but it was just to close this discussion, and that's it for what I wanted to say about large deviations today. So perhaps in the last few minutes, I'm going to try to motivate. So now I'm going to switch to a different topic. Starting from now, and in particular next time, we're going to start to discuss statistical mechanics, really. Okay, so I think it was important to make sure that everybody understands large deviations before we do this, because, yeah, I don't know, it doesn't make sense, I think, to do statistical mechanics if you don't know large deviations. in statistical mechanics, we will often be concerned with these probability measures I already discussed last time, called the Gibbs measures. Okay, and I'm not going to give you a full explanation for why this is a good notion, but today I'm going to just try to gesture at you why this makes sense. And if you want more details, there is in particular a concrete example that is being worked out in the very first section of the lecture notes, okay, where you can read in detail a concrete mathematical example where the Gibbs measure is going to show up naturally. I'm going to try to describe this example a little bit by waving my hands today. Okay? So let me see if I... Yeah, so, okay, originally I think the concept comes from physics, so I'm going to try to picture a physical situation. But as you see in the notes, this is not really necessary to make these Gibbs measures appear. So suppose you're looking at a physical system, and it can be in, let's say, a finite number of possible states. Okay, maybe I'm going to call it sigma if I want, because, okay, why not? Sigma is a good name for a state. And each of these states is going to be, it's going to correspond to some energy for the configuration. Okay, there's an energy associated with each possible configuration. And we are going to, like, basically, you know, if you imagine the, let's say, the objects in the room when they're at equilibrium, we have this intuitive sense that they are all at the same temperature. And I'm going to try to capture what that means by just gesticulating a little bit with my hands. So my preferred system, which is with this finite number of states, and the state is sigma, I'm going to try to think it's embedded into some sort of medium with lots of other objects, and for some reason it's going to equilibrate, it's going to exchange energy until they reach equilibrium in some sense. Okay, I'm kind of gesturing at your intuition a little bit. So perhaps just to make things simple, you can imagine that it's just surrounded by copies of itself. You know, because why not? You know, this is a valid other object. Okay, there are lots of copies. Maybe there's 1 million copies of this object that we like, and it's all there. They are all there together, and it's a physical system. The total energy is fixed, so we know that over these 1 million systems, the total energy is given. If I sum all the energies of each of these guys, this is a fixed parameter. We cannot change it. But among them, they can exchange energy. And for reasons I'm not going to discuss, let's postulate that it's a good model to assume that among all of the possibilities for spreading this energy around, they're going to pick uniformly at random. Okay, they have lots of choices. And you know, there are justifications for this, which I don't want to go into, but let's just take this as a postulate that among all of the possibilities, it's going to pick uniformly at random. Okay, so you have all of these states, you have this budget of energy, and you just pick at random uniformly one possibility. And you ask yourself now, you come back to your favorite object, and you ask yourself, what's the distribution of this object? You know, it has a finite number of possibilities. They are random because they are like the image of this measure. And the claim is that if you do the calculation, which is, you know, it's really a combinatory exercise, this is what is done at the beginning of the book, you're going to discover that this probability is a Gibbs measure, which means there exists a parameter, let's call it beta, such that the probability for you to find the object in configuration sigma is proportional to exponential beta times the value of the energy in this configuration. Okay, and this is how it arises. And you see the way I build this is really, you know, I try to discuss something about the temperature at the beginning, but it's a very generic phenomenon. You know, you don't need to worry about physical situations to find this an important information to have. You know, maybe, I don't know, you do some very theoretical study of your favorite function, and you know that the L2 norm is fixed, and you think about these Fourier coefficients, and maybe you think there are, you know, the energy is a bit spread out around all the Fourier coefficients. Maybe you're going to think, okay, maybe it's uniformly spread around all the Fourier coefficients. What's the distribution of one of the Fourier coefficients? Well, it's going to be the Gibbs measure. You know, that's how it is. Okay, so what else do I want to say? I thought I want to say something more. Maybe that's it. Gibbs measures. let me think. Let's double check. Ah yes, the last comment I wanted to make is I was almost hesitating to tell you in advance this intuition that when we put a bunch of objects into the same room and we wait for long enough, then at some point they are at the same temperature, because we are mathematicians, and it's kind of always a bit bizarre when you start to use words that you're not quite sure what's the definition of the word. What does it mean, temperature? And in fact, basically the sort of construction I gave you basically is going to lead you to the definition of the temperature. This beta that is showing up when you're doing this construction is by definition, in fact, the inverse temperature. And okay, that's all I want to say for today. So next time we're going to start discussing statistical mechanics, and I hope you will agree that Gibbs measures sound like a reasonable concept.